Hello students, from today we are going to start the videos of linear algebra. The first chapter is matrices and system of linear equations okay. We are familiar with the topic matrices, operations such as addition, multiplication of matrices. Okay. In this chapter, first topic is row echelon form and reduced row echelon form and reduced row echelon form. Sorry, this R is capital. Okay, echelon form of a matrix. Echelon form and reduced row echelon form of a matrix. Definition. This is a topic. The following three operations on the rows of any given matrix are elementary row operations. First is multiplying all the entries of a row. All the entries of a row by a non-zero constant. B. Interchange of any two rows. Third, multiplying all the entries of any row by a constant and the resulting products to be added to the corresponding entries of any other row. These are the three elementary row operations. First is multiplying all the entries of a row by a non-zero constant. Second is interchange of any two rows. Third is multiplying all the entries of any row by a constant and the resulting products is added to be the corresponding entries of any other rows. Okay. notation, these operations can be written as, if the rows of a matrix are denoted by R1, here I will write in short form, R1, R2 and so on, from top to bottom. These R1, R2, Rm are rows of the matrix. Then above these three elementary row operations can be conveniently expressed in the following manner. That is, first row operation is, what is first row operation is? Multiplying all the entries of a row by non-zero constant. Means, suppose this k is any non-zero constant, k into Ri. Means what? Multiplying all the entries of a row by a non-zero constant. What is second? Second is interchange of any two rows, means Rij. Rij means what? Interchange of any two rows. Third one is multiplying all the entries of any row by constant. Suppose k into Rj, and the resulting products be added to the corresponding entries of any other rows. Means Ri plus k into Rj. Okay. Means if R1, R2 and so on Rm are rows of a matrix, then we can perform a row operation k into Ri. Second is interchange of row, and third one is Ri plus k into Rj. Okay. Let us write down next definition. Next definition. Analogous to elementary row operations, analogous to elementary row operations, which are called elementary column operations. Elementary column operations as follows. If C1, C2 and so on, Cn are columns of a matrix, from left side, from left hand side to RHS means right hand side, then we have first is k into Ci, means k is not equals to 0, multiply ith column by a constant k. B, Cij means interchange of ith column and jth column. C, Ci plus k into Cj means multiply all the entries of jth column by constant k, add the resulting product to the corresponding entries of ith column. Okay. Let us write down one more definition. Given a matrix A, by applying a finite sequence of elementary row operations, we we obtain a matrix A dash. Sequence of row operations A to A, then and so on, means we are apply finite sequence of elementary row operations on A. This process of obtaining A dash is called row reduction or Gaussian elimination. Row reduction or Gaussian elimination. Okay. This process is called row reduction or Gaussian elimination. Okay. Let us take one more definition. A matrix A is said to be in reduced row echelon form. In reduced row echelon form if it has the following properties. If it has the following properties. First is, if a row does not consist of zeros, then the first non-zero number in the row is 1. We call this one as leading one. Second, if there are any rows that consist entirely of zeros, then they are grouped together. Then they are grouped together at the bottom of the matrix. Third, in any two successive rows that do not consist entirely of zeros, the leading one in the lower row, lower row occurs further to the right than leading one in the higher row. Fourth one is each column that contains a leading one, each column that contains a leading one has zeros everywhere else. Okay. See here, what is reduced row echelon form? For this, here are four properties. First is, if a row does not consist of zeros, then first non-zero number in the row is 1, and this one is called leading one. For example, suppose this is a matrix 1 0 0 1. Okay. In this matrix, this one is a leading one for this row, and this one is a leading one for this row. If here is 2, then this is a leading entry for this row. But if we want to convert this matrix in row echelon form, for that purpose, here is 2, and when it goes in row echelon form, if this 2 becomes 1. So here we have to perform a row operation R1 upon 2. Then this matrix will be goes in reduced row echelon form. Second is, if there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Means what? If you have a matrix 1 1 0 0 0 0 1 2 1, if you want row echelon form of this matrix, then you have to group together this row at the bottom. Means you have to interchange R2 and R3. Okay. Next is, in any two successive rows that do not consist entirely of zeros, the leading one in the lower row. See this example. Leading one in the, suppose this is a lower row and this is a higher row. Then what happened? Leading one in the lower row occurs further to the right than the leading one in the higher row. See here, this leading one is right to this leading one. Okay. And last is, each column that contains a leading one has zeros everywhere in else. Means what? See here, this one is a leading one for this column. Okay. This leading one is only leading one. Or this one is only non-zero entry in this column. Similarly, this leading one contains, similarly this column contains a leading one has zeros everywhere. Or for example, suppose 1 0 0 0 1 0 0 0 1. See here, this one is, see here, each column of this matrix contains a leading one. each column of this matrix contains a leading 1 and has zeros everywhere else. Okay, means what? Leading 1 is only non-zero entry in that column. Okay, these are the 4 properties for reduced row echelon form. Next definition is of row echelon form. Next definition is of a row echelon form. That definition is just a little bit change. A matrix having only the, say above or below, only the above 3 properties, only the above 3 properties, 1, 2 and 3 is called to be row echelon, is called to be in row echelon form, is called to be row echelon form. Means what? If matrix satisfies these 3 properties, then we say that matrix is in row echelon form. And if matrix satisfies these all 4 properties, then we say that matrix is in reduced row echelon form. For that, see some examples for better understanding. Example, the matrices matrix 1 0 minus 1 0 0 1 2 0 0 0 0 1 and matrix 1 6 0 1 0 0 1 2 0 0 are examples of reduced echelon form, are examples of reduced row echelon form. Okay. Why these matrices are examples of reduced echelon form? See here, for this row, a row has leading entry because this one is first non-zero entry in this row. Now this one is first non-zero entry for second row, and this one is actually this one is first non-zero entry in this row. Okay, so each column has leading one, means first property is satisfied. Here is no zero row, so second property, don't think about second property. Third property is in any 2 rows. If we think about these 2 rows, what happened? Leading 1 in the second row further to the right than the leading 1 in the higher row. Similarly, this leading one in third row occurs further to the right than leading one in second row. Okay, means third property is also satisfied. Now see here, for this column this leading one is leading 1, this one is leading 1, and for this column this one is leading 1. Each column that contains a leading 1 has zeros everywhere else, means only this one is non-zero entry in this column, otherwise all entries are 0. similar for here and similar for here. That's why this is a reduced row echelon form. Okay. Similarly, this matrix satisfies reduced row echelon form. That's why this matrix is reduced row echelon form. Okay. Next is the matrices. Matrix 1 4 3 7 0 1 6 2 0 0 1 5 and matrix 1 1 0 0 1 0 0 0 0 are examples of row echelon form. Okay. This row has leading 1, second row is also has leading 1, and third row is also have leading 1. Okay. This matrix satisfies second property, third property. Okay. So that's why this is the example of row echelon form. Similarly, if we think about this matrix, this one is leading 1 for this row, this one is leading 1 for this row. Okay. Means first property satisfies, or which row is 0 row is at the bottom of matrix. That's why second property is also satisfied. And third is, if we think about these two successive rows, then leading one in second row occurs further to the right than leading one in the first row. Okay. These are the examples of row echelon form and reduced row echelon form. Let us write down one remark. I just remark is the zero matrix and identity matrix of any order are trivial examples of reduced row echelon forms. Okay. Student, keep in mind that the zero matrix and identity matrix of any order are trivial examples of reduced row echelon form. Let us write down note 1. From above examples, it is clear that every reduced row echelon form is row echelon form, but not conversely. Means what? Row echelon form is not reduced row echelon form. This is a row echelon form, but not reduced row echelon form. Why this is? Because this one is leading one for this column, but this one is not only non-zero entry in this column. That's why every row echelon form need not be a reduced row echelon form. Second, if AII is equals to 1 and AIJ is equals to 0 for j less than 1, then 1 is leading 1. Then 1 is leading 1 or pivot position of Ri. If AII is equals to 1 and AIJ is equals to 0, for j is less than 1, then 1 is leading 1 or pivot position of Ri. Okay, this is leading 1 and leading 1 or pivot position of Ri. Okay, let us take one example. Let us consider example. Let us consider the matrix. Let us consider the matrix A is equals to matrix 1 minus 1 2 minus 1 minus 1 2 1 minus 2 minus 2 minus 2 minus 1 2 minus 4 1 1 3 0 0 minus 3 minus 3. Okay, see here we have to obtain reduced row echelon form and row echelon form of this matrix. Okay, this one is a leading one for this row. Okay, so here we require 0 0 0. For that we perform a row operation. Apply R2 minus 2R1, means 2 minus 2 is 0. Next is R3 plus R1 and last one is R3 minus 3R1. So our matrix becomes 1 minus 1 as it is 2 minus 1 minus 1. See here R2 minus 2R1. So that's why 2 minus 2 is 0. Means what? Multiply all entries of R1 by 2 and subtract from R2. So R2 minus 2 is 0. 1 minus 1 into minus 2 is plus 2. So this 1 plus 2 is 3. Minus 2 minus 4 is minus 6. Minus 2 plus 2 is 0. Again minus 2 plus 2 is 0. Okay. Next is R3 plus R1. Means 1 minus 1 is 0. Okay. 2 minus 1 is 1. Minus 4 plus 2 is minus 2. Next 1 minus 1 is 0. 1 minus 1 is 0. 3 minus 3R1 is 0. 0 plus 3 is plus 3. 0 minus 6 is minus 6. Minus 3 plus 3 is 0. Minus 3 plus 3 is 0. Okay. Now see here students, this is a leading entry for second row. But in reduced row echelon form and row echelon form, leading entry should be 1. That's why we perform a row operation 1 by 3 R2, or we can say that apply R1 1 by 3 into R2. So our matrix becomes 1 minus 1, 2 minus 1 minus 1, 0, 3 minus 6, 0, 0. Sorry, here is 1 and here is minus 2. So 0, 1, minus 2, 0, 0, 3, minus 6, 0, 0. Okay. So this is a leading one for second row. Yes, so here we require 0, here also we require 0. For that purpose, we perform a row operation R3 minus R2. Okay, R3 minus R2, and one more operation R4 minus 3R2. Okay, so our matrix becomes 1 minus 2 minus 1, 2 minus 1 minus 1, 0, 1 minus 2, 0, 0, 1 minus 1 is 0, minus 2 plus 2 is 0, next is 0 minus 0, this is 0, 0, 3 minus 3 is 0, minus 6 plus 3 is 0, and 0, 0, 0. Okay, suppose this matrix is R dash. See, R dash, this is a row echelon form. R dash is a row echelon form. Okay. Zero row in this matrix, 0 rows grouped together at the bottom. Each row has these 2 rows has a leading one, and leading one of this third row occurs right to the leading one in first row. So this is a row echelon form. Now we have to find out reduced row echelon form. For the reduced row echelon form, here we require 0, because in reduced row echelon form, a leading one in reduced row echelon form, each column that contains the leading one has zeros everywhere else. That's why we require here 0. For that, we will perform a row operation R1 plus R2. So we will get a matrix 1 minus 1, 2 minus 1 minus 1 as it is. R1 plus R2. So minus 1 plus 1 is 0. Minus 2 plus 2 is 0. Okay. 0 minus 1 is minus 1. Sorry. 1, because R1 plus R2, na? 1 plus 0 is 1. Minus 1 plus 1 is 0. 2 minus 2 is 0. Minus 1 plus 1, minus 1, minus 1. And second row as it is. So 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. This is reduced row echelon form of A. This is a reduced row echelon form of A. Okay. Let us take one example for homework. Example: reduce the matrix A to its row echelon for and reduced row echelon form, where A is equals to 2, 3 minus 1, 1 2 1 0 0 2 2 1 6. Okay, we will stop here. Thank you.